When can we say that an algebraic expression is a polynomial or a non-polynomial? Not all algebraic expressions are considered to be polynomials, but polynomials are, of course, algebraic expressions. Here, before we could give the degree of the polynomial, let's try to determine first whether these four expressions are polynomials or not. Because if they are non-polynomials, then we don't need to look for a degree of the polynomial. Then it would be easier for us to give our answer. To determine whether an algebraic expression is a polynomial or not, we need to understand that the exponents for the little coefficients should be positive integral. What do you mean positive integral? If they are positive numbers and they are all integers. And if they don't fit that characteristics or criteria, then definitely as a whole, they cannot be considered to be a polynomial. So if we talk about x to the power of 1 or y squared, if you see this in a term, then you might say that that term is a polynomial. But if you see a to the power of negative 1 or b to the power of 1 half, that would mean the polynomial the expression as a whole is a non-polynomial. Let's talk about number one first. Before we could say whether this is a polynomial or not, let's try to look at the literal coefficients. We have here three terms. This is a trinomial algebraic expression. But is it a trinomial polynomial? Let's see. The literal coefficient for number 2, since there is no variable here, there is none. There is no literal coefficient for the first term. For the second term, the literal coefficient is the variable that could be found there, and it's actually x. Again, we don't need to take the sign or the operation before as the sign, because if we talk about literal coefficients, we don't concern with whether it's negative term or a positive term. And for the third term here, you have x cubed. These are the literal coefficients for the specific terms here. Again, the first term is a constant. There's no literal coefficient there. The next, let's try to look at the exponents of the literal coefficient. This here is x. It doesn't have any visible exponent, but automatically it has exponent of 1. Here, the exponent is 3. And there are no other little coefficients here. So by looking with these two, both of them are positive and they are both integers. That would mean that as a whole, number 1 is a polynomial. And if it's a polynomial, we can now look at the degree of the polynomial. The degree of the polynomial can only be determined if we can determine the degree of each terms of the given expression. The degree of the term for each term is actually the sum of the exponents of the literal coefficients or the variables. Since we have three terms here, we can get the degree of a term for the first term. We have the degree of a term for the second term and the degree of a term for the third term. Why is this important to pass degree of a term? Because our task, degree of a polynomial, can only be determined as the largest or the highest degree of a term. So we need to get first the degree of each term and look at what is the largest value, and that would be your degree of the polynomial. Let's look at the first term. The first term doesn't have any literal coefficient. It's a constant. Hence, we have no exponent for the literal coefficient for the first term. This would mean that the degree of a term for the first term, being the constant, is 0. That is the exponent of the variable, or there is no literal coefficient there. And if there is, you could say x to the power of 0, because x to the power of 0 is 1. 1 times 2, it's still 2. That's why it's 0 here. Degree of the term for the second term is the exponent of the variable here x, which is 1. And the degree of the term for the third term is the exponent, which is 3. Out from these three, the largest is the degree of the term for the third term, which is a 3. And this is now the degree of the polynomial. Because then again, the degree of the polynomial is the largest or the highest degree of a term. That is how we determine the degree of the polynomial. Again, first, let's determine whether it's a polynomial. And if it is, let's get the degree of each term and decide what is the degree of the polynomial. To do that in number two, let's determine first whether the literal coefficients here, their exponents, will meet the standard. We have three terms, so we could expect here three different literal coefficients. The literal coefficient for the first term are all variables with including their exponents. You have m, n squared. For the second term, you have m cubed n. And for the fourth term, the third term, you have m and then n. Look at the exponents of the literal coefficients here. For the first term, you have m to the power of 1 n squared. For the second term, you have m cubed n to the power of 1. And for the fourth term, you have m to the power of 1 n to the power of 1. All of the exponents here are positive and they are all integers. This would mean again that number 2 is a polynomial. After determining that this is a polynomial, we can now draw down the degree of each term. Since we have three terms, as it is an example of a trinomial algebraic expression, we can get 3 degrees of a term, which will help us decide the degree of the polynomial. So the difference between number 2 and number 1 is that for number 1, we only have one variable or one type of variable for each of the terms as its literal coefficient. So we don't need to look for the sum. But here we have two different variables for each of the term as the literal coefficients. So to get the degree of a term, we need to add or sum up the exponents. So for number one, the first term, the degree of a term is the sum of the exponent of m, which is 1, and then n, which is 2. This is actually 3 because the proper definition for the degree of a term is the sum of the exponents. So for the second term, you have m cubed, that's 3, plus n to the power of 1, which will yield as 4. And then for number 4, you have 1, that's number 4, the third term, we have 1 plus 1, you have here 2. Among these 3 degrees of a term, your largest degree of a term is of the second term in the expression, which is 4. It is also your degree of a polynomial. That is how we answer number 2. Let's proceed to number 3. In number 3, we also have 3 terms. So that for us not to waste time, let's try to determine first whether this is a polynomial or not. So let's look at the literal coefficients. For the first term, you have here the literal coefficient x cubed over y. What does this y represents here? Take note that one of our laws of the exponents is the law of the negative exponent, which tells us that if I have an expression here with a negative exponent, I need to make sure that the exponent will be positive, and I'm going to bring it down, making a rational expression 1 over x. This means that whenever we see a variable in the denominator, it could be brought up with a negative exponent. And when we say about polynomial, the exponents should be positive. This means that x cubed over y could be rewritten as x cubed, and I'm going to bring up y with the exponent of 1, and then I'm going to make it negative so that when I return, it will become over y. One of the exponent is negative. This would mean that this term for the third expression is not a polynomial. Now, even if for the second term, its literal coefficient is x and then y to the power of 5 with exponents 1 and 5 both positive, and even if the third term is a constant with no literal coefficient, as long as one of the terms in a given expression is not a polynomial, everything as a whole is no longer a polynomial. This would mean the result for number 3 is not a polynomial. And if it's not a polynomial, why bother to get the degree of the polynomial if in the first place it's no longer a polynomial? Of course, you could try to get the degree of each term. Okay, as the sum of this will become 2, probably you could say the degree of a term for the first term is 2. Here is 1 plus 5, you have 6. And for the last term is 0, same as number 1, a constant. But in the first place, it's no longer a polynomial. So why bother in doing that? Again, what makes an expression not non-polynomial is when we have negative exponent. Or just like this, we have a variable in the denominator. And finally, if we have square roots or with fractional exponents. What do you think now is number 4? Sir, in number 4, I see square root. Will this mean that the expression is non-polynomial? The only restriction to decide whether it's a polynomial or a non-polynomial is the literal coefficient. Look at the square root. It is part of the numerical coefficient. It did not exceed here. This would mean that our a here is not part of the root symbol, and it doesn't fall to this. Therefore, we could say our literal coefficient for the first term is the simply a, but not square root of a. It's just a. In the second term, sir, you also mentioned that there should be no fractional form of the variable. But why is it that there is a fraction here? But look at the denominator. The denominator is not a variable, it's a constant 2, or in short, it's 1/2. So still doesn't meet the consideration for non-polynomial. And it's because the literal coefficient for number 4 is b cubed. Looking further at their exponents, a to the power of 1, b cubed, both exponents are positive and integers or integral, we have here a polynomial. Again, the only consideration for an expression to be a non-polynomial is when there is a variable in the denominator for rational expressions, or we have a negative exponent, or we have here a root symbol with a variable inside it. But in number 4, it's already a polynomial, so we could look for its degree of the first term and degree of the second term. Whatever would be the larger between the two, that's your degree of the polynomial. Even if we have different variables here, we only have one variable per term, or one literal coefficient per term. That would mean we just simply look at their exponents, and exponent here is 1 for the first term, exponent here is 3 for the second term. The largest is 3. That's your degree of a polynomial. Again, in number 3, you don't need to look for the degree of a term or degree of a polynomial, because in the first place, it's no longer a polynomial. It will just not help your cause. This is how we determine the degree of the polynomial for algebraic expressions. Goodbye, everyone.